Is the screen visible?
Yes, sir.
Okay, so what we are trying to do in the theoretical aspect of learning, see, the goal of learning is how we perform in an unknown data set. That is to minimize the out of sample error by the hypothesis that you have learned. So your goal is the red one. E out G should be tending towards 0. To achieve this goal, we followed a deviated route of having two things. That whenever we train, we make E in equal to 0, and that we covered to a larger extent with all our learning algorithms that we have studied. We tried to make the in sample or the training error to be 0. The second thing, we then assume that the concept of induction learning assumption says if we sufficiently approximate the in sample error and make it less, it will also make the out of sample error less, because in sample error tracks the out of sample error. So first part is the learning algorithm that did it. Stochastic gradient and all tries to minimize the error with your hypothesis and pick up the best hypothesis. The second part is the concept which we call as the generalization, because how well you learn the training, the error that you minimize during training, it should also apply to minimize the error while testing or the unknown data. So therefore, can this out of sample error with your hypothesis may be tracked by the in sample error with the hypothesis? So this is the feasibility of the learning questions, and we end up with this feasibility of learning that bad thing can happen, that it does not track well, is bounded by a probability value. Since it's bounded by a probability value, we have a hope that we could learn and or the learning is feasible. However, we get a very big factor here, M, which is the number of hypotheses. And in perceptron, like simple perceptron learning algorithm, we have seen that this hypothesis number is actually infinite, because we are heading towards a continuous space of weights, and we can take any of the continuous real value. Since any possible hypothesis can happen, this makes it as a big M, because this probability bound is calculated based on the non-overlapping bad events, since we added all of them. So to make it more generalized in learning, we need to reduce this somehow. Yesterday, we started to give an intuition that not all the hypotheses are completely disjoint. They have a vast portion or a significant portion of overlap. And that's why we say that the hypothesis H1 here in the figure and hypothesis H2 is basically overlapping in so much that the difference of this tracking of the hypothesis H1 is almost equal to the difference of the tracking of hypothesis H2. They differ only in the green sets. Hence, our assumption that this big M comes from the non-overlapping hypothesis space is actually in practice not applied. So with this notion, can we replace this M with something lesser? Then we started to think out loud that, let's say, this is our actual space where the blue line is the true unknown line that you need to discover. So what we can see, you can only see through an opaque sheet these points. You do not see this line anymore. You have to fit your own line to make this approximation of this line, which is your G. Now, if you can see that there could be many lines without changing the level of the point, as you can see in this figure, that H11, H12, H13, nobody changes the level of this point, whereas H22, H21 changes the level of this point. So we thought that maybe these categories of lines which does not change the level has a significant overlap in the hypothesis space, whereas the lines which are changing the level of the training points may have less overlap. So what if we consider all those lines which are not changing as contributing once in this hypothesis? In other way, what if you just look at only the points and try to figure out how many different constellation of such points can happen with the n training examples? What it will help? It will help to reduce the infinite space into looking at your training points. And this does not lose the generality, because you can only see the training points before you reason out about a learning. You do not see what is actual. The actual is unknown to you. Therefore, with the respect to the training points, if you could figure out how many possible way I can color these training points into two different colors, which is in term, which is we call it as a dichotomy, or how many dichotomy of such points exist. So this top is one type of dichotomy, this is another type of dichotomy. In this way, how many of them exist, that may be a quantity to replace m. Though I am going intuitively now, I will immediately prove it theoretically, maybe in today's class or in the next class. That maybe this intuition of counting the number of dichotomies may help us to replace this quantity. Let us try to look a bit more details on this dichotomy issue. Our hypothesis is basically a continuous space. It's a function from a continuous space of x, the full input space, to +1 or -1, as we are dealing with two classes. The dichotomies, on the other hand, are only looking at the endpoint. Therefore, the number of hypotheses that you can get could be infinite, because the number of hypotheses in the original input space is the placement of this line, and there are infinite number of placement of this line can be possible. Whereas if I only give you these endpoints and ask you how many dichotomies can be possible, it could be at max 2 to the power n, because each point can take two colors, either blue or red, right? So therefore, the maximum number of dichotomies can be 2 to the power. So this, in fact, we call it in another terms, we call this as a growth function as well. And since it's dependent on the number of points, so it's a function of the hypothesis which gives me the maximum number of different constellation of these points. It is indeed important that what is our challenge? Our challenge is that I give you a, you give me most bad possibilities of these n points in your input space, such that they can take maximum number of hypotheses or maximum number of different colors. This is indeed important, because when we say maximum number of different color realized by these endpoints, means that your hypothesis space is most generic with respect to that constellation of the point. Okay, so suppose that I give you these 6 points as shown here. If you place it in one line, then by a linear separator, you cannot get all possibilities, right? Rather, if you place it in some kind of arbitrary position, maybe you can get all possibilities of colors in these points. So I give you n, you give me your way of making those points in the worst possible manner, so that the number of different constellation of points gets maximized. So in a way, what I am trying to do, this MHN, if I try to formalize, is trying to maximize with respect to the points that I give it to you, these n points from the input space. It tries to maximize the number of hypotheses or the number of dichotomies possible with respect to the placement of any points anywhere you like. Okay, so that's our goal, and we believe that this may be a quantity which can replace m. As I said believe, because I have not proved it yet. So let us look into this growth function much example or a bigger details. So as we can know n points, we have known an upper bound of it. It's a 2 to the power n, which may not be significant, but it's significant over infinity. 2 to the power n looks much better than infinity, but is it always 2 to the power n, or it can be less than that? We need to see. So let us take an example of 2D perceptron. Suppose I give you 1 point. So what will be the number of dichotomies you can make with two classes? Can you tell me how many number of dichotomies can we make with the two class?
Two.
Two, because I can color it red, I can color it blue. Therefore, I can make. If I give you 2 points,
Four.
because if I put a line here, both of them will be blue. If I put a line here, both of them will be red. If I put a line here, this could be blue, this could be red, or vice versa, right? So 4. What if I give you 3 points? There could be displacement, there could be displacement. So what if I give you 3 points? How can you place it so that I get maximum number of dichotomies? How many of them? Look, if I
8.
place a line here, yes, if I place a line here, all of
Three.
them are no. See, if I place a line here, all of them could be plus one, plus one, plus one. If I place a line here, all of them will be minus one. Each of the point, if I place a line like this, it could be plus one and other could be minus one and vice versa. And I could place this, I could place this. You agree? So all possibilities I can have. So this is 8 in the maximum. However, as I said, it's your choice to place the point in the worst possible manner, because if you place the point this way, it is not the worst possibility, because in this way, you cannot get such kind of a leveling with the linear separator. Agreed? With one single line, can you get this level as plus one, minus one, and plus one? Or can this be blue, and this be red? Can it happen?
No.
No,
No, sir.
because you cannot separate it. So this is not the worst. This is the worst possibility. This is not the worst. I'm saying not worst. So therefore, MH is the maximum number of dichotomies that you can get with n points that you are choose to place. What about 4?
16.
How can you realize this one? Can you realize this one? If this is blue, this is red, and this is red. Can you realize this point?
No.
Similarly, if the level flips, if this is minus, you cannot. So two constellations you cannot realize by an arbitrary placement of this point. Any way you place, you will see two constellations you cannot realize. If you want to place it worse than this in further corners, you will not. If you place it in a single line, you may be more, you cannot realize. But my job is to place it in such a way that the maximum I can realize. You can see that here, two of them I can not realize with respect to 16 minus 2 is 14. Everybody are with me? What we mean by number of dichotomies?
Yes, sir.
So you
The
can
last
see
part
here,
is not clear.
last part is that I give you 4 points, right? In which way you can place it so that you will get maximum number of labelings of the points of the dichotomies. So
Hmm.
any way you place it, there will be this constellation that I have shown here. You cannot realize by separating with one line. Agree or not?
Yes, agreed.
Similarly, if the plus was minus and the minus was plus, that configuration also is similar. You cannot realize.
Hmm.
So
Yes.
two of them you cannot realize, right?
Yes. Yes. Yes.
Among all possibilities. So as
Okay.
you can
Okay.
see, it is for 2D perceptron in general. As if you grow, you will see it is not 2 to the power n, but something less than that. Which makes sense because 2 to the power n is a huge quantity. But if we could make progress with that, that will be very nice. So let us see some other simpler example. Suppose I give you a line, and you need to figure out which position the separated line point is. Beyond right hand side is all plus and the left hand side is all minus. In a way, you need to figure out where is this point, that beyond that this one is plus and the left side is minus. So how many number of dichotomies can be possible if I give you n number of points? in a positive ray line.
N plus 1.
N+1.
How do you get it? Because I can place A here, I can place A here, I can place A here, up to here. So there are n points, there are n plus 1 positions where I can place A. And each of the position will give you a different constellations of points. Agreed, everybody?
Yes, sir.
So here it is n plus 1. This one, positive interval, meaning that within A and B, I will color it as this, and beyond it, both sides are the different negative level. How many constellations are possible, or how many dichotomies are possible? I need to find an interval as my hypothesis. So how many possible intervals can I get in this endpoints? If I give you endpoints, how many possible intervals can you give it to me?
So NC2,
9.
we
No,
can
no.
select any 2 point
How do you
for
get 9
interval.
for
Hmm?
NC2? How do you get NC2?
Sir,
We
I
can
think
select
9.
No, not only for this point. I'm saying for n points. How can you get
Oh,
9 as
n
a
points.
constant? Yeah.
No, no, for this figure, I think 9, but for generalized n, it is.
So it's N into N
See,
plus 1 by 2.
absolutely. Why you are doing it? Let's say how many ways. So there are how many ways I can choose 2 points, because my 2 points are the interval. So there are 1, 2 up to n plus 1 number of points, and I need to choose 2 among them. This is one. But what do you miss? You miss the interval being within this range, or maybe within this range where every point is negative. You miss this one. Get it? How do you choose an interval? So you have to choose a point between n minus 1 separating positions. So sorry, n plus 1 separating positions. So n plus 1 positions, you need to choose 2 points. So anywhere you choose, it is your interval. So there can be anything. Anywhere you choose these 2 points between the separating positions, it's your interval. Now, what do you miss? That your interval could be fully left of whatever points you are given, or could be fully right in whatever points you are given. Beyond the interval, everything is negative. That is only one constellation. So this is the number of constellations possible, or the dichotomy is possible. Agreed?
Sir, in the interval, we can assume any number of node, color
Yes.
of points, or just fixed 4, as in this
No, no,
picture.
no, no, no. You need to give your hypothesis as A comma B. AB is anything. The question is, how many possibilities are here? See, here you didn't ask the question that should I fix the A here? Then your question is 1, 2, 3, 4, 5. That I didn't ask. I said how many ways you can choose to choose A to make this coloring different. So this is one particular constellation. If you have chosen A here, it is another constellation. Similarly, if you have increased the length here, this node will be green. That is another constellation. So how many such
Okay.
dichotomy or the constellation possible? It is this
Oh,
much.
okay, 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 okay.
Okay. So now you see the beauty that sometimes we may also, there is a chance that we may also land up in a polynomial quantity in this growth function. Not always it goes on exponential. However, there is an anomaly is that in this convex set, so by convex we mean that if you take 2 points and join them, they will pass within the boundaries of the region. So this is non-convex because these 2 points, if you take and join them with a line, you can see that it goes out of the boundary and then comes in. So this is not convex. Whereas here, any 2 points you take, it must be within the boundary. So now you do not see this region, but if it is a convex set to be learned within this constellation of points, what will be your MH? I give you n points. You choose your way to place it so that you get maximum number of dichotomies. What is that maximum number on the function? So first of all, try to think that with n points, if I give you n points, what is the worst placement it could happen so that I get maximum of this? Anyone? Take a circle. Place the point here at the boundaries. Your n points, try to place it in the boundaries. Now let's say this is one constellation, because in this case you may assume that your convex region be like this. This is +1, 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 and this is your -1s. Right? This is one constellation of the points which gives you this kind of a coloring. So therefore MHN, and enough hints now. What is MHN? What will be my MHN? N points, I place it, I thought that circular placement will be bad, and I place it in a circle where I will make the convex region with joining the points that are blue. How many different constellation can I get? How many different colorings of these points can I get? Isn't it 2 to the power n? You can get any color here, any color here, right? Because you are only joining the innermost positions of them. Any color in any manner, if it is also interleaved red blue, it doesn't matter because I'm just joining it. Yes or no?
Yes, sir.
So this is again coming to be exponential, and the worst case where this is equal to in our growth function. So as you can see that one thing is for sure, that if MH be the quantity that will replace it, if we believe that MH could replace something, if it is polynomial, it is better, because if you remember the equation, see this quantity, if it becomes polynomial, if I replace a polynomial MHN, as in case of positive rays or interval, such kind of a function, then if your error rate is not significantly large, let's say I want to do it within this error, if your n is huge, if I give you lot of training example, since it's e to the power minus, so this will dampen the fact of a polynomial. So there is benefit in generalizing if I can find two things. One, my growth function is polynomial. Two, our belief that growth function will replace m. Agreed till this point?
Yes, sir.
Yes, sir.
If you agreed, then let us go again with the fact that growth function is basically a function. So you need to compute for every n. If I give you one something, if I give you two, it's very cumbersome, because unless you get a closed form, say in case of perceptron, you need to go and compute and try to find a closed form. If it doesn't exist, it's a function, so you need to compute. Rather, what if in the theoretical advance, what if I could make such kind of a key notion that I can tell you a number, okay, which I will call is at a breakpoint. If I can tell you a number, if it has a breakpoint, then I will say that obviously your growth function will be polynomial. That will help because unless we have to compute this function again and again, I will tell you a number which is a breakpoint. And this breakpoint, if it exists, then I can prove that the function growth function will be polynomial. So the notion of breakpoint becomes that the breakpoint of perceptron is here, where beyond the number n grows. So breakpoint of perceptron, I say k, the breakpoint is 4. This is called the breakpoint. Because beyond the number or from the number 4, I started to get my benefit. Agreed?
Yes, sir.
That's what the definition of breakpoint would be. So if I can say that, so what is the breakpoint of this one? What is the breakpoint of positive ray? If since we computed this one, now it is good for us to just explore this. If n equal to 1, then mhn equal to 2, which is 2 to the power 1, not a breakpoint. If n equal to 2, then this is 3. Yes, it is less than 2 to the power 2. The breakpoint is 2. Agreed?
Yes,
Yes,
sir.
sir.
What is the breakpoint of this? Well, more computations you get. 1, it is giving, okay, 2, 1 is giving 2, 2 is giving 4, 3 is giving 4c2 plus 1 is 6 plus 1, 7. Yes, 7 is less than 8. Get it?
Yes, sir.
What is the breakpoint of this? Nobody makes it less than 2 to the power n. So it is the value of n which makes mhk less than 2 to the power k. That's the definition of breakpoint. So here no k, value of n makes it less than 2 to the power n. So we call this thing as that it is shattered by n. Just look at the term here. It's very colloquial term in machine learning. We call it shattered by n. So here, if someone has a breakpoint 4, I say that this particular 2D perceptron can be shattered with 3 points, cannot be shattered with 4 points. So its breakpoint is 4. Here I could be shattered with 1 point, cannot be shattered with 2. Hence its breakpoint is 2. Here it could be shattered with 2 points, cannot be shattered with 3. So here it cannot be shattered, it can be shattered with all endpoints. There is no way I can make it lesser. So the breakpoint is infinity. Now, since we knew this formula, it is easy to compute the breakpoint. However, actually in practical case, we will not see this formula. As you see in the perceptron, we do not know the formula. But it is easy to compute the breakpoint in an iterative manner, growing from small to big. You get my point. Even if you do not know the formula, just take this example in a positive way. So 1, yes, I can color it +1, I can color it -1. 2, well, I cannot color 2 as -1. I can color 2 as -1 +1, but I cannot color this. In case of 2, you cannot color it this way, right? Because it's a positive ray. If your interval is here, both of them should be blue, right? So therefore, the breakpoint is 2. You get my point, what I am trying to reach. Yes
Yes,
and
sir.
no.
Yes.
So instead of computing the whole function, breakpoint computation is easier, first of all. And breakpoint is the point k where the particular learning algorithm can be shattered with k minus 1 point, but cannot be shattered with k points. Then k is my breakpoint. Okay. Okay, so with this intuition, where does our theory lie? First of all,
Sir, I have a question. In the previous slide, in the figure number 5, we maybe had position like figure number 4, means the points are in linear. In that case, we cannot realize it using single line.
yeah.
So we should reduce
No, the
one
thing is
more.
that this is not worst. Rather, this is the worst. So you choose worst possibility of your endpoints. It is not the best you can choose so that to minimize MHN. You get the definition of growth function says that the maximum number of dichotomies you can get by your own bad possible choices of endpoints. This is the best possible choice.
Yes, sir.
That's what
Uh,
that's why it is 8, not this is not the constellation that I wished for.
yes, sir. But I was talking about figure number 5. If
This one.
the yes, for if the arrangement is like that, means points are linear, means red,
Then it will
blue,
be lesser
and
than this. Then it will be lesser
then
than this.
it should be 13, right?
Yeah, then you compute, but then MH is not usually 14 because MH is the maximum, right? If it is linear, then it could be much less than that. If it is linear, it could be much less than that.
Okay.
Okay. So we have reached a long point. First of all, we have reached a point where we have seen that this is less than equal to 2 to the power n. This is a potential candidate for n. Second, we have found that there is a notion of breakpoint k, and we have that notion when we can say that mhk is strictly less than 2 to the power k. Okay, and we say k minus 1 can be shattered. We call this term shattered. Then k is your breakpoint if k cannot be shattered, but k minus 1 can be shattered. With this intuition, we should not forget two things, that we need to prove these two things. Number one, if breakpoint exists, this imply MHN is polynomial, which we assumed to be nicer, but we need to prove. Second, indeed, MHN can replace N. Right? Here we stand now. Are you with me? So we are now in the premise of theoretically showing these two things. Okay, yes or no?
Yes, sir.
So in the corollary, you can also see that if breakpoint does not exist, which means if the breakpoint is infinity, then it's a 2 to the power n is your MH. Okay, as we have seen in case of convex sets. So to realize it more, as we can see that if I give you a breakpoint, what does, so let us first start to prove one, but before proving it, just let me give you an intuition that how existence of a breakpoint can make MH polynomial. So suppose I give you 3 points x1, x2 and x3 and tell you that that particular learning algorithm that you will give has a breakpoint of 2. Okay, the breakpoint of 2 meaning that you cannot have this or you cannot have two consecutive reds or two consecutive blues in the leveling. So this is prohibited. So therefore, if you give 3 points, what are the potential levels can you have? So I can have this as red, this as blue. Sorry, I just make a mistake. So let me tell that the two consecutive red, this is prohibited by the breakpoint. So I can have this and this could be blue. This can be red. This could be blue. This can be red. This too could be blue. But can I have any of the 2 points to be blue? No, because I have prohibited by my breakpoint two consecutive points cannot be blue, cannot be red. This and this cannot be red. This and this cannot be red, or this and this cannot be red. So that's the notion of breakpoint induces. As you can see here I have prohibited the factor that this red and this blue cannot occur together. Similarly, here the concept of breakpoint may be so that if I prohibit this, then you can only get these four constellation or dichotomy, these five constellation or dichotomy of the point, nothing else. Are you agree with that factor?
Yes, sir.
So therefore, you can see earlier you have 2 to the power 3 or 8 number of constellations. However, assigning a breakpoint to or a restriction that this is to be prohibited, it reduces drastically to 5. It reduces drastically to 5 and no more can be possible. So in a way, such a restriction, what does it impose is two factors. One, it reduces.
So red, blue, red is allowed, I think.
No, because I do not allow 2 points to be red.
Okay.
It reduces the 2 to the power n space, which is obvious, as you can see, drastically it reduces. Secondly, a theoretical phenomenon that if k be a breakpoint, so does k plus 1 too. It's trivial, right? Because if k is a breakpoint, then if you have k plus 1, just kill one, that will also give you a breakpoint, isn't it? If 4 is a breakpoint for perceptron, then any 5-point constellation is also a breakpoint, because 5 with 5 points you will obviously get less than 2 to the power 5 number of combinations. Agreed? Yes or no?
Yes, sir.
Because any level you give, you just kill 1 point. That will give you maximum with the 4-point levelings. So anyway, you can go doubling this level. So you cannot go much beyond that. So therefore, with this, we can see that it reduces the 2 to the power n space and shrinks it in such a good manner that it is indeed worthy to prove whether there is a breakpoint, how much does it reduce, and whether it's a polynomial or not. Right? That is our next quest. So let us go by this proof now. That the statement is like this: if k is a breakpoint, then MHN is polynomial. So to show MHN to be polynomial, we will go by this way, that we will first show MHN less than equal to some quantity, which is less than equal to some quantity, which is less than equal to a polynomial. This will show if MHN could be bounded by a polynomial, then it could be shown. So this is step 1, we will show it. This is step 2, we will show it, and finally we will bound it. Okay, this is how we will go in our proof. So let us say that b n comma k is the maximum number of dichotomies with n points having breakpoint equal to k. That is just for mathematical notion. I just say that b n k. So therefore, as you can see, this is the maximum number of dichotomies with 10 points having breakpoint k, and this is the quantity that we want to estimate and evaluate as mhn, which is a polynomial. Right? This is what we want to establish as less than a polynomial. Agreed or not? I mean, just I am trying to do it in BNK because I will do it recursively. And as you can understand, that recursive definition must have a parameter. In program, you also wrote recursive programs and you got it. Right?
Yes, sir.
Okay. Let us see the points now. In recursion, what is happens, you know that suppose I have this constellation of n points. In recursion, I just leave one and recurse over the others, right? So I first, so remember that this n points has a breakpoint k. Okay, I need to figure out what is the growth function. Is it is indeed a polynomial or not? So therefore, I need to count with this n point and k being a breakpoint, how many number of constellations are there, right? I count it in two different ways. I count it in two different ways. One is S1, another is S2. My counting would be like this. So since x1 to xn, since x1 to xn is one constellation, so it could have +1, -1, +1 like that, +1. This is +1. Some other -1, +1, -1, -1, so on, -1. This may be -1. Agreed. So such kind of things are there. So among them, I am trying to count how many such possibilities can happen with the n number of points that is given to me. Agreed. This is my BNK that I'm trying to compute. Are you with me till this point?
Yes, sir.
I divide this S1 and S2 in such a way where the extension xn, see, if I divide this, each of the possibilities can have +1 as xn, can also have -1 also as an xn, right? Either of them can happen.
Yes.
Or
Yes, sir. Yes.
now the question is, if the breakpoint is k, maybe some points do not have either a +1 or -1 associated with it. Some point can have both with respect to all the xn -1, but some points may or may not have, because I have a breakpoint. Not all 2 to the power n combinations are there. Agreed? If the
Yes, sir.
number of combination is less than 2 to the power n, some extensions xn could be +1 only. There is no -1 can be present in this set, or maybe -1, no +1 can be present in this set. Do you agree to this point?
Yes, sir. Agreed.
Therefore, my S1 set are those points where the xn's are only +1 or -1, not both for all values of x1 to xn -1. The remaining can be divided into two ways, that for the same entries of x1 to xn -1, I could have both +1 as well as -1. I divide it. So this is all those entries where xn could be only +1. There is no -1 counterpart with the rest. These S2 are all set of entries where there are two counterparts, both are present in this listing. Agreed with my division, everybody?
Yes, sir.
Good. So now I have to count them. So let's say this is alpha, this is beta, then this is also beta, because this is plus 1 and minus 1. Same number of items will be here as well as here, right? So I need to find out this. Clear?
Yes, sir.
Now to find out this one, I will do a trick. First I will find out what is alpha plus beta. So to find out alpha plus beta, I am drawing a box. You just concentrate over that box only. This is my alpha plus beta. Only with these box, the number of points here, the rows here are the alpha plus beta, right?
Yes.
Yes, sir.
Having k being the breakpoint with n points, can I say this is less than equal to b n minus 1 k?
Yes, sir.
Why?
If k be the breakpoint of all of them, right?
Hmm.
So
Yes.
what you took here? You took here only
Plus one
the
or minus
single
one?
extensions you removed, the single extension you removed, and
Hmm.
those extensions you kept here, which does not have a minus 1 counterpart into it. So if
Hmm.
you take only this orange box, these
Hmm.
points are also shattered with k breakpoint. Can be shattered
Yes.
with less than k, because I only removed the unique entries from the nth points. So that does not change my breakpoint here with this n minus 1 points.
Yes, sir. Yes, I got it. Huh? Thank you, sir.
Definitely it will be less than n minus 1 k. Good.
Yes, sir. Yes, sir.
Now I will try to find a bound for beta. Now I will urge you to concentrate on the white mark part only. This is my beta length. Just concentrate on this white part here, all of these rows. Can I not say that this is indeed bounded by, I mean, this is obvious, because if this is k is a breakpoint of those, this, so I kill all the entries which are extended by the unique extension, not by the both, and took one extension, then obviously k minus 1 should be a breakpoint. You can prove it by the counter by the counter proof of the combinatorial argument. If it were k, then adding both plus 1 it does not make the breakpoint of the whole set as k. You agree?
Yes, sir. Agreed.
So this beta number of items here would be less than equal to this. The number of dichotomies here maximum will be bounded by this. Why this one? This one is obvious because we have n minus 1 point. Why this one? If it were more than that, if it were k, suppose it were k, then with n points, since I added plus 1 and minus 1 both to the same entry here and here, therefore that whole set could not have k as my breakpoint, which is a contradiction. So it must have to be k minus 1 as a breakpoint. So now what these, with respect to this, what these two suggest? These two suggest that b and k must be less than equal to bn minus 1 k plus bn minus 1 k minus 1. Agreed?
Yes, sir. Agreed.
So where does it heading to? Let us see with the table, where does it heading to? It's a recursive definition, as we can see. So suppose this side is my k and this side is my n. So n may be 1, 2, 3, 4, 5. K may be 1, 2, 3, 4, 5, 6, and let's say this way. So with that, let us try to fill up. What is n equal to 1, k equal to 1? You can see obviously this side 1, 2, 3, all of them would be 1 because my breakpoint is 1, k is 1. Right? If my breakpoint is 1, you can only shatter 1 point. Isn't it? Yes or no?
Yes, sir. Yes, sir. Yes, sir.
Breakpoint is 1. That is the answer. Every if you increase n also, it doesn't change if my breakpoint is 1. Right? The number of dichotomies you can get in every position is 1 here. Here with 1 having a breakpoint of 2, that means the number of dichotomies you can get either a +1 to this point or a -1 to this point. 2. If you increase it also, since n can only take 2 levels, if you increase it also, it will remain as 2. Do you get the point? Because what does it mean by making a breakpoint higher number, that is the number of dichotomies to be more than it can be possible? Number of possible dichotomies with 1 point is only 2 plus red or blue. So with 2, this entry now you can, this entry is n minus 1k and n minus 1 k minus 1. So these two will sum up here, right? Then if k is more than the number of point given, so maximum I can get is 4. Now you can see this 2 will come here as 4, this 2 will come here as 7, and here again k is more than 3, so this is 8. This 2 will come here as 5, this 2 will come here as 11, this 2 will come here as 15. It's a binomial kind of a relation, it seems, isn't it? Pascal triangle.
Yes, sir.
So this is this part we prove, this part. The second part that we are going to prove is this is less than equal to sum of NCI where I equal to 0 to k minus 1. As it's a binomial nature, so I can fancy this by mathematical induction. Try to prove it, it's very simple. You can see it here, right? By mathematical induction, you can prove it. Yes or no?
Yes, sir. Yes, sir.
It looks a binomial, right? Because every time you see that it looks like a Pascal triangle, you're adding up this two, adding up this two, adding up this two, making the next row. It looks like a Pascal triangle. So a binomial estimation is a good estimation for this. And with this estimate, just go for mathematical induction with this plus this is less than equal to, you will get exactly this one. It's just a jugglery, it's just a calculation. So this is the second part that I am not proving it. I know you are quite equipped enough to apply induction principle here. You assume this and this to be some value, add it up, get this value, nothing else. Arithmetic juggling. So we reached at a point where MHN is bounded by for a breakpoint k. Isn't it polynomial? Because it's order of n to the power k at max. Or rather n to the power k minus 1 at max. Right? This is order of
Yes.
n to the power k minus 1, isn't it?
Yes, sir.
Are you all with me or totally lost?
Yes, sir. Yes, sir. No.
Yes,
Everybody?
sir.
Okay, you are. It's a simple computation, nothing else. So just to repeat in a brief manner, this one is the only extension for xn. This one is have the both extension for the values of others. Divide it into it. So the total number of rows is alpha plus 2 beta. Alpha plus beta is bounded by this because alpha plus beta are all those points which have different extensions here. So it should have a breakpoint k. Whereas beta, if you kill the other part of the beta, which has a minus extension, only take the plus extension, this beta should have a breakpoint k minus 1. If this is not the case, then the overall breakpoint should not be k, contradiction. These two gives us this summation. This is part 1. So MHN is bounded by this. Now this, since it is bounded by this, when I go for computing it in terms of a table, I found a binomial kind of a feeling. That feeling gives me to apply mathematical induction and get rid of this formula, which is the second part, which indeed, therefore, it's bounded by a polynomial, because at max from I equal to 0 to k minus 1, it will be multiplied n into n minus 1 into n minus 2 up to n minus k plus 1. That is, n will be multiplied k minus 1 number of time. Therefore, it's just a order of n to the power k minus 1. Since k is a breakpoint, it's a constant, it's a polynomial. That kills the proof. Okay.
Yes, sir.
So, just to finalize our today's lecture, just take this positive rays. What do we get for MHN? We get for MHN is n plus 1. Isn't it less than summation? So we got a breakpoint of this. Remember, we got a breakpoint of this as 2 positive rays. So isn't it I equal to 0, k minus 1, which is 2 minus 1, right? And this is my NCI. This is equal to n plus 1. So it's very tight. This bound is very tight in case of whatever we produce by our combinatorial argument. Positive interval. I will just finish it just by giving these examples. That's it. We get the positive interval as n plus 1 C2 plus 1. So this is half n square plus half n plus 1, because this is n plus 1 C2, which is less than equal to, and I have seen that the breakpoint of this is 3. So which is basically I equal to 0 to 3 minus 1 NCI. And it is indeed
পার্সেলটা দেখে দিয়েছে তো
excuse me, someone is not muted, I think. So, yeah, thank you. Yeah, so this is what we got for the positive interval, which means this is also, you will see that it is also very tight, because we get it, if you elaborate this one, this side, it will be same as this. However, in case of 2D perceptrons, things are really interesting. If we get 2D perceptron, then we do not know about the function, right? But we know the breakpoint of 2D perceptron is 4, which means this is basically 1/6 n cube plus 5/6 n plus 1. So which means that, see, 2D perceptron is a very simple model, isn't it? It's a very simple model, very simple learning model. And it is obviously polynomial in terms of a growth function. That means that probability of E in minus E out is bad is bounded by this. If it is bounded by this kind of a polynomial, so this is basically very much damping, because this is just a n cube factor, whereas this is e to the power minus. So if your n, the number of examples, the number of training examples are huge, then you have a reasonably good generalization bound. Do you agree? So the next question is that, can it replace M, which we will tackle in the next class. So we need to prove that really can MHN replace M. That's the question. Okay, we need to prove this one too. I hope I could dilute the flavor of computational learning, and it's proved by something with first intuitively presenting it and then trying to prove it formally. That's it for today's class. Thank you. If any quick questions, otherwise we are 2 minutes ahead of time. Okay, thank you. Let me stop the recording.